the infrastructure that we have at NPSF, National Param Supercomputing Facility. And I would try to touch upon various aspects of the entire system and ecosystem. And the session is more of kinds of informative and would address your some of the common issues and doubts that you have. So let us start. So NPSF, as the name says, it's a National Param Supercomputing Facility, and C-DAC established this NPSF with a mandate to offer the state-of-the-art high-performance computing systems to various institutions and industries that need such a facility to process their diverse applications and resources. It was with that one more mandate was there that we should help them with the know-how of usage of such systems and proliferate the HPC awareness in the country. With that mandate, the NPSF has come into existence in 1998 with the establishment of Param 10,000 supercomputer, which was 1.6 gigaflops performance at that time, which was offering 1.6 gigaflops of performance that time. And after that, subsequently, then it came Param UA, which is a 54 teraflop system. That system came in 2008 and was commissioned in C-DAC's university campus. That system was having a CPU only system, and it was having cluster of workstations architecture. The system after that, in 2013, we have upgraded the compute capacity of Param UA to 10 times of its current capacity. So earlier it was 54 teraflops, and now then we have upgraded it to 524 teraflops. And the Param UA2 was India's first hybrid system. It was having many integrated cores, Xeon Phis as the accelerating cards. And then we were having 220 such nodes, and the peak compute power was 524 teraflops. The system ranked 69th in the top 100 list of supercomputers in the world at that time in 2013. The journey with Param UA2 continued till 2020, and after that you can see that we are with Param Siddhi AI, which is dense GPU infra, and is being offered to the nation as a compute platform. Okay, so let us see what Param Siddhi AI and the subsequent machines are. So the Param Siddhi AI, so it's a 5.26 petaflops. Peta is 10 to the power 15, and flops is floating point operations per second. That is a double precision performance of the system. The mixed precision performance of the system is 210 petaflops, which also we call it as AI petaflops. Okay, and in 2020, when the system was commissioned, the Param Siddhi AI system was commissioned, it ranked 62nd in the top 500 list of supercomputers in the world in November 2020. This was the highest ever ranking that we have got in the when we have commissioned and benchmarked the Param systems. Okay. So this system was made available to academia, MSMEs, and startups and industries as well. The system continued to operate till 2023. And in 2023, considering the dire need of more and more computing resources, especially more and more GPUs users required to perform scalability to carry out scalability of their applications, and were in need of expansion of the compute infra. So with that, we have augmented the compute capacity of Param Siddhi AI to almost double of its current capacity. Earlier it was 210 AI petaflop, and we have added 200 AI petaflops more of compute. So it's now the system, now the total compute that we have is 410 AI petaflop. Okay. We were having 42 number of DGX A100 compute nodes as the part of Param Siddhi AI, and we have added 40 number of more such nodes to the Param Siddhi AI system under the system AIRAWAT POC. And with that, now we have total 82 number of DGX A100 systems with mixed precision performance of 410 petaflop and a double precision performance of 13.17 petaflop. So the name, as the AIRAWAT is there, it's actually proof of concept system, which is first phase of the AIRAWAT project. So under the AIRAWAT project, it is envisaged to establish an exascale system in C-DAC. Okay. So this being a first part, we have established this 200 AI petaflop system as the proof of concept in AI research analytics and knowledge dissemination platform, which we are calling as AIRAWAT. With the commissioning of AIRAWAT POC system, we have integrated Param Siddhi AI with AIRAWAT POC. And then after the successful integration of the system, we have carried out the benchmark. So benchmark is a very well-known and widely and globally accepted high-performance link-back benchmark, which performs double precision matrix multiplication, and is a benchmark being considered to make your system rank in top 100 list of supercomputers in the world. So we have successfully carried out that benchmark. And we have received 8.5 petaflops of maximum performance with a peak performance of 13.17 petaflop of the system. So we have this 410 AI petaflop mixed precision, and now what we achieved is 8.5 petaflops of double precision performance. With this 8.5 petaflop of double precision performance, which we got in the benchmark, we got a 75th rank in the top 100 list of supercomputers in the world, and we got a #1 rank in India. So this AIRAWAT-PSAI, AIRAWAT Param Siddhi AI, this integrated system is #1 in India, and it's 75th in the world. Okay. This ranking we got in the 61st list of top 100 supercomputing list, which was published in International Supercomputing Conference ISC 2023 in Germany. So this is a certificate being issued by top 500 association, and there you can see that we got the 75th rank with the 8.5 petaflops of double precision performance, sustained performance. The diagram or the architecture diagram that you see here, it's actually the architecture of AIRAWAT POC system. Okay, so here you can see logically the diagram is divided into two parts. One, the upper part, the upper green box, is actually the current architecture or the infrastructure that we have with us. So on the left side, you can see that the existing Param Siddhi AI system with 42 numbers of DGX A100 nodes. And on the right side, you can see the newly commissioned AIRAWAT POC system, which is having 40 numbers of DGX A100 nodes. These two systems have been integrated with the help of a director switch, the InfiniBand director switch. And we have a common parallel file system based storage, which is a 10.5 petabytes of storage, is made available on both these systems. So with that, we have integrated the system. In the next phase, we have the plans to now further augment the capacity of this system because the current infra is catering to the training workloads only. So you must be knowing that the DGX A100s that we have, they are being extensively used and are supposed to be used only for training the data sets or carrying out the HPC workloads execution. But considering the need of having infra for inferencing and ancillary services and the requirement of having it with a cloud-like semantic, we have the second phase of the system, which is going to come shortly, which is a GPU-enabled cloud infra for inferencing and ancillary services. It is soon going to be commissioned, and the beauty of the coming infra is that the existing 10.5 petabyte storage is going to be made available on the this cloud computing nodes via this NFS protocol. So if you must be knowing that in case of AI workloads, so the major two phases are training and then followed by inferencing. The trained data set is required to be made available for inferencing. So currently users are kind of downloading their data sets from the system, and then they are again copying that data set back on the system they're again copying it back on the system where they are having their inferencing carried out. So to mitigate that issue, now the upcoming infra where we are directly going to make those data sets available to the systems for carrying out the inferencing. User need not to explicitly copy the data sets in and out of the system. The upcoming system is supposed to have 20 numbers of again 800 GPU enabled nodes. Each node is going to have two number of 800 GPUs, and such 20 nodes we are going to have. So we are going to have actually we are going to have a CPU as well as a GPU infra available with us, which is going to be offered as a cloud infrastructure and for inferencing services as well. So this infra is also going to have its own 2 petabytes of storage, which is going to be a unified storage and is going to be offered in NAS as well as iSCSI protocol based. So this combined, let us have a look at the stats of the system. So this combined Paramsiti and AIRAWAT-PSAI system, we have total 629 users with us, and they are actually carrying out 176 numbers of projects. The users belongs to 114 different institutions, like various academic and premier institutions, including industries, MSMEs, and startups. The system has successfully processed more than 150,000 jobs on the system till now, and with the mandate that we have, we should have more and more startups and MSMEs with us. So currently we have 14 startups with us, and many more are on the way to be onboarded with us. And through this session, I would like to appeal to all those, including startups, who want to have account on our system or would like to access our system. They are welcome to approach us, and we are just an email away. The system, to reiterate, that we have 8.5 petaflops of performance that we got, and 13.17 as the peak performance that the system has. This is how our user base is spread across various research domain, applications domain. So you can see on the right side, you can see machine learning, deep learning, NLP, computer vision, video processing, and any and similar other domains related to AI. And then on the left side, you can see that various HPC domains are also listed. So the purpose behind showing this slide is that we are catering to the needs of various HPC and AI application domains. So users belongs to various domains here. The point to be noted here is that more than 45% of the users, they belong to AI community, and they have been carrying out their executions of the workloads on this system successfully since its commissioning. Going deeper into the system architecture or the system components. Here you can see that we have this major components like compute nodes, director switch, then this edge switches, and then storage. Okay, so the system is having 82 numbers of A100 DGX A100 compute servers. That's a major what we can say, it's a major component of the system. And then we have InfiniBand HDR 200 director switch with us, and these compute nodes are connected to this connected to the director switch through the InfiniBand network. We have 10.5 petabytes of PFS based storage, parallel file system based storage, and it is also being offered it is being offered over InfiniBand fabric on the compute nodes. We are going to go into more deeper in this architecture, but this slide was to show you the major components that are participating in the that are major parts of the AIRAWAT-PSAI infrastructure. So when we say this 800 compute nodes, we have 82 in number. Each node is having 256 CPUs. So total 20,992 CPU cores in total that we have with us. When we talk about the major component, which is a A100, DGX A100, so we have 656 A100 GPUs in the system, because we have 82 systems and each system is having 8 number of A100 GPUs. When we talk about the interconnect, we have for the compute communication, means node to node communication, we have this 8 number of InfiniBand connections per node, and such we have of 82 nodes. So the switch that you see, the big cupboard like switch, rack like switch, that switch is actually we have connected all the compute connections to the switch. Okay. We are going to go into the details of the switch as well. Regarding the storage, it is being offered over InfiniBand through a separate fabric and is made available on the compute nodes through again InfiniBand, but a separate switch and its architecture. That also we are going to see. And of course, the storage that we have is having a performance of 250 gigabytes per second with 4 million IOPS, random read IOPS. The storage that we have is a 2-tier storage with us. Now, going into the deeper of the AIRAWAT-PSAI architecture, though it looks slightly complex, I will try to make it simple and easy to understand. The top right section you can see is AIRAWAT-PSAI compute nodes. So they are arranged in row and rack fashion. Okay, and to these AIRAWAT compute nodes, the compute communication network, which we were calling as InfiniBand HDR, the green colors ones. Let me just pick up the cursor. Please wait. So this is our main compute infra, and to this compute infra, you can see that the green colors, thick lines, they are so now it should be visible more more clear. So this is a compute infra that we have. Okay, to this compute infra, these nodes, these 82 nodes are interconnected by a very high speed and low latency interconnect. We call it as InfiniBand. So the speed of each link or each connection is 200 Gbps, gigabits per second. So these two green thick lines represent the compute communication, the compute network connectivity within, across these nodes, and all these compute cables are connected to this director class switch. So we have total 648 HDR 200 cables being connected for the compute communication. And here you can see login node. Here also we have 8 cables connected. So it is actually total 82 into 8 numbers of HDR 200 InfiniBand connections connected to this director switch. Okay. So this green colored connections, or the InfiniBand HDR network, that is explicitly being used for the inter-node communication, wherein it's a node-to-node communication. This network is being used for exclusively. And the orange colored one connected to the compute infra that you can see, that network is nothing but it's a storage delivery network. So our 10.5 petabytes of 2-tier storage is being made available on these compute nodes through this HDR InfiniBand connection. But this network is separate than the compute network. So the orange color connections you can see are the storage networks, and the green color connections that you see are the compute networks. The storage, so you must be knowing that during this commissioning, we have actually isolated the storage and the compute. So we have now separate storage island. We have created a separate storage island, and the storage is offered through a separate dedicated storage fabric. This not only helped us in scaling the storage, but also it helped us to maintain, to remove the dependency on this director switch. So if this director switch fails in the worst condition, the cluster operations won't stop. Your storage would still be available on the compute nodes. Only restriction would be that multi-nodes jobs will not run. The jobs would run well within a compute node because of the availability of the storage and other services. Non-availability of this director switch is not going to impact on the operations on the or the availability of the cluster. So that was the main purpose behind segregating the storage fabric from the compute fabric. Earlier, we were having storage connected to the same director switch where our compute fabric is also connected, but now we have separated it. Now this is on the left side you can see there is a storage network, which is actually nothing but connections of 40 port switches, 10 numbers of 40 port switches connected in a fat tree topology. And so one more beauty of this topology or the architecture that we have is no single point of failure of the storage. So it will never happen that due to failure of one of the network switches or one of the connections to the storage is not available. That thing will never happen because of this new restructuring. Okay. So at the bottom right side, you can see one 10 GBE switch, which is a switch exclusively or the network exclusively made available or commissioned for acting as an orchestration network. So all our system services, ancillary services, for example, Slurm or authentication services, they all communicate through this dedicated 10G network. So that's why you must be seeing the compute node names as, for example, SCN1-10G and so on and so forth. Okay? Because this compute communication, because this Slurm communication is happening over a dedicated orchestration network. So you can see at the left top, user has to access the system through VPN, and then it will land on the login node and will access the compute resources. We have a separate session on this, how to actually access the system through the VPN in the later sessions. So just to complete the architecture, I have added this user part as well. moving forward. Now let us go in more deeper in each of the components of the NPSF AIRAWAT-PSAI infrastructure. The first and foremost, which we can call it as the heart of the system, is these DGX A100 machines. We have those in 82 in number. Each system is having 8 number of NVIDIA A100 GPUs. The diagram that you see is the actual slightly animated, but the actual this is how these components look. Okay. So the arrows that show is 8 numbers of NVIDIA A100 GPUs. These A100 GPUs are connected with each other with the help of 6 number of NVIDIA NV switches. The CPU part, we are going to go into the deeper of how they are actually connected. Here, the purpose of the slide is to give you insights of various components of the A100 system. So 8 number of A100 GPUs connected through 6 number of NVIDIA NV switches. And then we have 2 sockets of CPUs. So each with 64 core. The CPU is AMD ROM EPYC 7742 CPU. So we have 2 such sockets, each with 64. And when the threads are enabled, now each system you can see 256 CPUs. Okay, so 256 CPUs and 8 GPUs that we have in each compute node. The memory available, the system RAM that we have is 1 terabyte, and these systems are interconnected through 8 number of Mellanox Connect 6, means the 8 number of interfaces. So these systems are connected with each other through this IB HDR 200 Gbps interfaces, 18 number. The 9th one is for storage. So looking at the specification, we have 8 NVIDIA A100 Tensor Core GPUs. Total GPU memory that we have is 320 gigabytes because we have 8 GPUs and each GPU has a 40 GB memory. Okay, so in Param Siddhi AI and in AIRAWAT POC, we have 40 GB A100 GPUs. So total GPU memory that you see per node is 320 GB and 8 number of A100 GPUs. The performance of each node is 5 petaflops, which is a mixed precision performance. Okay, and because it's a 5 petaflop per node, such 82 node gives us 410 AI petaflops. So these GPUs are connected through NV switches, which are 6 in numbers. Looking at the power consumption, so system requires a very huge power, which is a 6.5 kilowatts. So these are we can say that these are the power hungry systems, consuming the power at the range of 6.5 kilowatts. The CPUs are AMD EPYC 7742 128 cores, and after threads enabling threading, then we have 256 cores, each clocking at 2.25 gigahertz, and clock boosted it will go till 3.4 gigahertz. The RAM, the system RAM that we have, CPU RAM that we have is 1 terabyte, and the networking is 8 number of 200 Gbps interfaces for compute communication and 1 interface, HDR 200 interface for storage communication. And apart from that, we have this 10 Gbps Ethernet Ethernet port that we have, that we are using for carrying out our orchestration services. Okay. In the previous slide, one thing I forgot to mention is that we have in-band and out-of-band management network as well on the compute nodes. In-band being the management of the nodes through Ethernet through operating system. So that we call it as a management network. Generally, you must be using SCN1-MN. So that MN is nothing but our management network, which is an in-band 1 Gbps Ethernet network. And then apart from that, we have out-of-band management network, which is actually a remote management network. So we can in the absence of non-availability of the operating system or the LAN, we can even remotely power on, power off, or of the remote management API ILO These are the different names of the system of this network. So we have those networks as well with us. It is just that the diagram, the architecture was becoming slightly complex, so thought of removing it from the architecture. So we have seen that from the networking, it has 8 compute networks and 1 storage network. The operating system that these 800 systems is actually DGX OS, which is a proprietary operating system by NVIDIA based on the Ubuntu. So most of the packages are kept, and some of the packages are removed from the Ubuntu based DGX OS. So it's a basically can say customized operating system for these DGX 800 systems on NVIDIA systems. The storage that we have locally available on the 800 nodes is actually 1.92 terabytes of M.2 based NVMe storage, wherein the actual DGX OS, which is the operating system, is being configured in RAID 1. And then we have another storage which is actually 14 to 15 terabytes of storage available in so based on this U.2 NVMe drive, and can be used as the local storage. So we have a slide on that as well. Looking at the weight of the system, it's a very heavy system. To say it weighs, only the node weighs 125 kilograms, 123 kgs. So it's actually a very risky and mammoth task to move these nodes in and out of the racks of the in the data center. So to carry out these movements of the server, we have a data center lift, which actually moves these servers in and out of the rack and helps in mounting and doing the maintenance. When we so you can see that the faceplate, the golden colored faceplate is there, which is the front of the node. When we remove that faceplate, you can see the front side of the node like this. So here you can see 8 number of fan modules, okay? And then the bottom section is having 8 numbers of disks. So the top section is nothing but the fans to actually pass the air or cool the systems, okay? And the bottom section here we have the storage to be made available, storage from where the operating system and the local storage also comes. When we look at the back side of the nodes, these nodes, you can see there are 3 parts. One is a GPU board tray, the upper part is GPU board tray, the middle part is the the system board or the motherboard tray, and the bottom part you can see that there are 6 power supplies of the nodes. So logically these nodes are actually divided into 3 parts. So let us go further deeper, and let us look at this CPU board or the motherboard tray. So this is a more what we can say more what I can say expanded view of the motherboard or the CPU tray. Here you can see the 4 number of 4 number of adapters at the left side, marked by this green rectangle, and also you can see 4 numbers of adapter marked in green at the right side. So these are the total 8 number of adapters. Okay, and these 8 adapters are actually basically connected to the director switch and are actually part of the compute communication network. Okay. So these 8 rails, we can call it as rails. So it's a multi-rail system. So these 8 rails are connected to a director switch. Each rail is having 200 Gbps. So each port, in each port, a separate 200 Gbps cable goes, and such 8 cables goes just for the compute communication or the inter-node communication. So with this, the total compute bandwidth of the node of a compute communication bandwidth offered by the node is 1.6 terabits per second, 200 Gbps each, and such 8 connections. You can see this adapter pictures are pasted over here. So NIC 2, NIC 3, NIC 6, NIC 7, NIC 0, NIC 1, NIC 4, and NIC 5. And on top of that, we have the logical. On top of that, we have this logical names of the NICs, which are actually named as MLX5_2, MLX5_3, MLX5_8, MLX5_9, MLX5_0, 5_1, 5_6, and 5_7. So these are the names of the logical names of these adapters. These actually, the purpose behind mentioning these in this much detail is that it has a direct connection to the topology awareness or the topology of the system. Okay, so please keep in mind that these are the 8 connections which are used for the compute communication, and these are the names of the NICs or the network cards. Okay, on the left side you can see one more rectangle, and the top port of this rectangle is actually marked in the orange color and is representing again the storage network. We have one more port for the storage network, so this port is optional whether we want to use it or not. The bottom side you can see that we have 2 more LAN ports. LAN means the Ethernet ports. One is the one which is marked in green is for out of band management. So in the earlier slide, I have mentioned that there is a presence of out of band management network, wherein we actually manage these servers remotely. We can manage these servers remotely. So that port is for that purpose. And the right side port, which is where it is written as LAN, that port is actually our management network. So the left side is management network, the right side is out of band management, the left side is in band management. Apart from that, then we have a dedicated orchestration network. So this port is actually catering to the orchestration 10G orchestration network, where our system services and other orchestration services runs. So this is actually a rear view of each of the DGX A100 compute node. So going in more deep into the topology of this A100 system. So this diagram very well depicts the connections or the basically the connections, how the GPUs, NVLink, and the CPUs and the NICs or the adapter cards, they are interconnected. This understanding of this topology will help users to actually further gain more performance, because you will profile the application, you will optimize the application according to the topology awareness. So that would actually somewhere it will help you in gaining more performance and would also help in optimizing the application. So here in this diagram you can see that there are two CPUs, means 2 sockets, CPU 0 and CPU 1. Actually by default actually it's a 64 core, but after enabling threading it is 128 cores. So CPU 0 is having 128 cores and CPU 1 is having 128 cores. These 2 CPUs are divided logically into 4 NUMA domains. NUMA is non-uniform memory access domains. So those NUMA domains are named as 0, 1, 2, and 3. And similarly on the CPU 1 they are named as 4, 5, 6, and 7. Now, to the odd number of these NUMA domains, we have this PCI switch is connected. Okay, so you can see this PCI switch and this PCI switch. And to this, each of the PCI switch, we can see that two GPUs are connected. So to this PCI switch, we have GPU 0 and 1. And the adapter that is connected to the same PCI switch are MLX5_1 and MLX5_0. When we look at the bottom side of the topology diagram, we can see that all these 8 GPUs, they are interconnected with us with the help of NVLink and NV switches. So basically, you can see that these lines, colorful lines, are nothing but NV links, and these green boxes are nothing but NV switches. So each GPU is connected with other GPU with the help of NVLink, and the bandwidth, the bidirectional bandwidth between GPU to GPU is 600 gigabytes per second. Okay? So the inter GPU communication happens through these NVLink and NV switches at the rate of 600 gigabytes per second. However, this the adapter cards, that these Mellanox adapter cards or the NIC cards, okay, they are connected with GPUs through these PCI switches. So you can see these 4 PCI switches. Okay. So in order to so the traffic in and out of this GPU has to come through either the MLX5_0 NIC or has to come through MLX5_1 NIC. Why it is so? The advantage here, if we actually choose to pass the traffic through this MLX5_0 and MLX5_1 for GPU 0 or GPU 1, the main advantage it offers is that they all are connected to the same PCI switch, and then traffic, the data transfer or the transfer of the traffic need not to pass on through the CPU. It need not to pass on to the CPU. It will directly will be passing through the PCI switch. So we are avoiding the hope of the CPU. Okay? So that's why when you are choosing the GPU 0 or GPU 1, please make sure that you also simultaneously choose NIC 0 or NIC 1, which with the logical ID of MLX5_1 and MLX5_0. Suppose you want to have a communication between GPU 0 and GPU 4, then you have to altogether pass through the CPU. Sorry, you want to have the traffic pass from MLX5_6 NIC and to the GPU 0, then you have to pass through the CPU. Okay, because it's altogether on a different, connected to the different socket and to the different NUMA domain as well. So this topology will help you to optimize the communication and will help you to improve the performance of the system. So here actually you can see that to the NUMA domain 0, you have these storage NICs connected. Okay? NUMA domain 0 and 4, and NUMA domain 1 and 3, you have GPUs and these compute communication networks are connected. So how we can see this topology? So you just have to execute a command NVIDIA SMI topo -m. So by executing this command, you will see the matrix kind of representation, which shows you the actually connectivity, how they are connected, how the GPUs and the NIC cards, these are the NIC cards and these are the GPUs, how they are interconnected with each other. And the second last column that you see is what are the CPUs which are connected to it. So this being slightly a complex representation, or the complex, what we can say, the connection, we should refer to this table, which actually gives you the summary of how the affinity has to be. So if you are selecting a GPU with ID 0, please make sure that you select the CPUs from the NUMA domain 3 and you select the IB device as MLX5_0. Similarly, if you are, for example, selecting the GPU ID number 4, which actually we represent using a CUDA visible devices. So if it is 4, then please select the CPUs with a NUMA ID or the domain ID 7, and the IB device corresponding to it should be selected, should be MLX5_4. These details are also available in the DGX A100 user guide, where these optimization settings are also available to understand. I hope this affinity and topology is clear to everyone. Let us move further. So further major component of the system is the director class switch. We have been talking about this director class switch, and this is how it looks actually. So the right side of the box is the front view of the director class switch, and the left side of the box is the rear view of the director switch. Here you can see these blue and red connections. So they are nothing but they are the coolant in and out connections, which are connected to the spines of the switch, and this metal frame is nothing but it's a manifold of the switch. The bottom side, the bottom server like device that you see is nothing but cooling distribution unit. So actually the switch that we have is a liquid cooled switch, okay? And there is a separate unit which is a cooling distribution unit, which actually takes care of cooling the switch by passing the coolant through the leaves of the switch, through the spine and leaves of the switch, and it regulates the flow and the pressure and the temperature of the coolant which is being circulated to the switch. So in the director switch, we can see that there are 20 numbers of leaves in it and 20 numbers of spine. So basically concentrating on the leaf side, leaves is nothing but where actually the compute communication links are actually going to the leaves of the switches. Okay, so we have 20 numbers of such leaves, each is having 40 ports. Okay? So total 800 ports in the director switch that we have. And this is a backside view of the coolant distribution unit, where you can see that these connections are made for in and out of the coolant of the switch. So the switch that we have, when we have commissioned, it was first of its kinds of installation by NVIDIA, first of its kinds of newly released switch, and it was first of its kinds of installation being done at C-DAC by NVIDIA. Okay. So the switch was, it's a state-of-the-art switch. The name is Quantum CS8500 modular switch. 800 HDR 200 ports that we have, 40 ports each leaf and such 20 leaves. And and we can actually what we can split each link into two 100 Gbps HDR 100 links. So if we do that, then we get 1600 such links out of the switch for connection. So different 1600 devices can be connected to this single switch. The switch is offering aggregate switch throughput of 320 terabits per second, which is a very huge bandwidth of performance that this switch is offering. The cooling is it's a liquid cool, like I told, that is a coolant distribution unit, and that the switch weighs 747 kg, and it actually occupies a whole rack. So this switch is actually being used for all the internode communication. Next major component that we have is a storage. So we have 10.5 petabytes of 2-tier storage, which is actually made available through network on the compute nodes. Okay. So that storage is offering 250 gigabytes per second, and it's a hybrid storage made of NL SAS disks, which are NL SAS disks, and then other are the SSDs, the flash disk or the SSDs. So collective capacity of the storage is 10.5 petabytes, and the performance is 250 gigabytes per second, and 4 million random IOPS is the performance of the storage. that is being made, the capacity is 10.5 petabyte and is made available as NLSAS. It is made available under the mount point as NLSAS, NLSAS FS, where actually when the user logs in, his home area and entire his data resides on this 10.5 petabyte network shared storage. One more storage that like I iterated earlier, that's a node local storage, which is actually a 14 terabytes of storage, which is it's a NVMe disk based RAID 0. It's actually storage is made of collection of 4 disks combined, offering a capacity of 14 terabytes, and the performance that is offered is 25 gigabytes per second. These disks are connected in RAID 0 fashion, and it is also supposed to be a fast storage and is expected to be used during your computations as a local storage. Okay, so maybe some writing some intermediate data, you can use this storage during the job run, during the computation. So it's actually available under /RAID mount point, and is expected to be used by the users. However, you have to make sure that you actually copy back the data generated under /RAID to your home area, which is under NLSAS FS, immediately after your job ends or as part of the job's ending processes, because after your job ends, the data is going to be vanished. The data is going to be basically erased, because the same storage then have to be made available for the further jobs that are going to be executed on those computers. So you can very well use this storage, which is a node local storage, for writing your intermediate data. Moving further, so till now what we have seen is mostly the hardware aspects of the system and various components of the system. Now let us move towards the software environment that we have. So you can see this is a stack diagram. The bottom layer is the 10.5 petabytes of Lustre parallel file system, the storage that we have on the system, being made available on login nodes as well as all the compute nodes, where actually your home area and entire all the packages and all resides. Okay. Then further to that, then we have this storage actually delivered over InfiniBand. So HDR 200 InfiniBand communication network for storage as well as for compute, separate networks are there. That layer is there. Then on top of that, we can see there is a layer of DGX-OS, which is actually a proprietary operating system being offered on top of this. After that, then there comes NVIDIA GPU drivers and runtime. So basically, you must be seeing that various utilities regarding the GPU access and the what we can say the runtime libraries are also there. So that layer is NVIDIA GPU drivers and runtime. On top of that, all the frameworks and tools and libraries and HPC applications, AI frameworks, workflows, everything resides on that. So Ajay was just listed some of them, few of them. So even the MPI or the CUDA, all these tools, libraries, frameworks, application, everything resides at this layer. Going one layer above, then we have the environment that caters to both kinds of workloads. One is the bare metal workloads, and another is the containerized workloads. So we do encourage running the applications through the containers. The containers that we have are the en route containers, which are the rootless Dockers. Docker we do not encourage. We encourage en route as the container type. And then we have our scheduler, which is a Slurm scheduler, which is integrated with this en route with the help of some POAxis libraries. So basically, through Slurm, you can actually execute en route containerized images you can run and execute on multi-node, multi-GPUs as well. The right side, you can see that we have these system related services, like we collect the logs from the system for the various services, and then Slurm logs and other authentication service logs and all. We also have our monitoring and management softwares associated and are sitting at one layer. And then we have some admin services like DN, LDAP, then proxy we have, then network time sync, email services. All these are the admin parts of it, which actually plays a very important role when we call something as a cluster, or the what we can say entire system. Okay. We have also given access to the NGC, NVIDIA GPU cloud, to the users, so they can directly log into that NGC and can directly download the containerized images of the applications and convert them into en route. These things will be even covered in depth in the upcoming sessions. But point to be mentioned here is that we do not maintain a local repo. However, the connection to the Docker Hub or the NGC is open for everyone. So let's move further. So these are the few snapshots taken from various management, monitoring, and dashboards. So the left top that you see is the dashboard that represents the stats of the system. So we do have that, and we do the live monitoring and assess the stats of the system. We also actually the left bottom that you see are the utilization stats, utilization graphs of the system. Like you see a gap between April and May, which was our pay period wherein we commissioned AIRAWAT POC system, and that's why the data is not there. So you can see we also monitor the usage of the system. The top right is the monitoring tool where we actually monitor each and every parameter of the compute nodes going to the node level. And the right bottom section is this screenshot I have kept to show you that we also do monitor temperature and power, which are actually out of band parameters for the compute nodes through our monitoring. So these are the different levels of monitoring that we do, which help us to actually look at the overall health of the system and keep the system to its healthy state. So we do have even alerts enabled to these monitoring tools, so that if something goes wrong, we immediately get the alert over email, and then accordingly the action is being taken. So this is the monitoring of the director class switch. The top, the left side that you see are the front and back representation of the director switch. The leftmost is the front view of the switch, and these green squares that you see, green rectangles and squares, are actually nothing but these are the LEDs or the indications. Each that rectangle or the brick shows the connectivity. So if any of these links are disappeared or are in amber in color, then we immediately assess that it has some issue. Okay, so this is a live monitoring of the director switch. The top right side you see is the InfiniBand fabric management and monitoring system that we have. And the bottom side, right bottom side that you see is the storage monitoring, where we monitor the performance of the storage, the capacity, the IOPS, and the health of the storage. Going further, in this workshop, I know that many of the participants must be having a question that how to be part of this NPSF, or those who would want to have access to our system and are not part of the NPSF. This slide is basically targeted for them. That we have something called as technical affiliation scheme, wherein we actually we actually want that the users be part of this NPSF technical affiliation scheme, and so be it a startup or MSME or industry, academia, they all are actually invited through this session that they be part of this infra and carry out their competitions and get benefited. This let me explain the process as to how a prospective user can become technical affiliate and can access the system. The prospective user has to just send us an email, so npsf@cdac.in, and they have to specify basically that they want access to the system. In response to the email, our team, the dedicated support team, would ask them the standard questions regarding what compute infra that they require, compute storage infra, and what kind of projects and tools that they require. That's a preliminary assessment that we do, and from where the user belongs and all. Once we get those details from the users, we assess that, and based on the assessment, then we if it is felt that the requirements that the users have can be catered using this infra that we have, then we send them something called as a technical affiliation scheme form. The user has to fill in that form, and the form is very descriptive and covers various aspects which we require to be maintained as part of our records, and also help us to actually know what kinds of requirements that the user has. The user has to fill in that form, basically mentioning brief details about their project and the compute infra that they require, the storage, and any other tools that they require. So duly filled and signed form, the user has to send us a scanned copy, and we then further take that filled and signed form, and we once again do the verification, and after verification we send that form to the authority. There is a committee and authorities that have rights to actually go through the application and whether to approve, disapprove, or have some comments. So those higher authority, they approve the request. Then if it is approved, then we create the accounts on the system and communicate the access details and through our welcome email, and also provide them the various advisories and our user manuals. And then later on, we actually are with them throughout the user journey with us actually. So we have a dedicated team who takes care of right from onboarding to the various issues if they have been faced. So this is the overall technical affiliation scheme process. So this, even we are encouraging more and more startups to be onboarded with us. And if you have your colleagues or friends who are part of startups, we actually appeal or request that you please circulate these to them so that they can be part of our National Param Supercomputing Facility. So these are the charges of the compute resources that they have. These charges have been derived considering the various global scenarios and the other service providers which provide the GPU infra. These charges are very competitive as compared to the ones that are offered by the other service providers like GCP or Azure or AWS. Okay, and these charges are actually per GPU hour basis, and the charges are for each NVIDIA A100 GPUs. Okay, and the beauty of this system, or the charges, why they are so economical and are affordable, that on the other cloud service providers, you must have seen that the charges are levied from the time the GPU instance has been initiated, and even if the GPUs are not being used and you are just copying the data, but just because you are actually instantiated the instance and the GPUs are live, you will be charged for that duration as well. Whereas here in our case, you will be charged only during the execution of your workloads on the GPUs. I mean to say that whenever the compute job accesses the GPUs, only till that duration you will be charged, and you will not be charged for your logins, for data copy, or for accessing compilation, nothing. You will be only charged during the actual executions of the GPU, or when your actual batch job starts and ends. Only that batch job runtime, for that only we are charging for the GPU usage. So that is why these charges are very competitive as compared to other service providers. We have all the infra at our place, and we do have a dedicated support with us, and we don't charge for all this support or other ancillary like bandwidth and all. We are not charging. We are charging exclusively only for the usage of these 800 GPUs. And then there are further discounts based on how you reserve the GPUs. And you can see that for 1 year, it is 50% discount which is being offered. Moving further, the existing NPSF users must be receiving, especially the chief investigators of the projects, must be receiving these statements of accounts every month in the first week, or mostly on the first or second of the every month. So let me clarify a few things from this statement of account. First of all, this is not actually an invoice. It is not an invoice against which the payments have to be made. These are actually for the awareness of the users and to give them the utilization details on a monthly basis. So this actually has details. If you see the first page, top left side, you can see that there are the details of the CI, Chief Investigator of the project, and then their institute address, email address, contact number. There on the top right side of the first page, then we have the invoice period and when the project has started. In the middle of the first page, then that you see, it's a summary of usage and the charges which are applicable. So basically, you must be as I mentioned, we are charging only for the 800 GPUs, and the storage consumed beyond 1 terabyte, we are charging at a very minimal rate. So the consumption by that particular project in that particular month is being highlighted in GPU hours. You can see that these are the GPU hours being consumed under this project, and then we have a charging rate, and accordingly the charges are calculated, and they are in e-money. They are not the actual INR, they are e-money. Similarly, additional storage, if someone has asked, then we are only charging for the additional storage, and then summing it up and rounding off, then we get the total e-money which is being consumed by a particular project in the particular month. Then we also brief upon the number of users that we have in that particular project and the number of jobs that were executed under that project throughout the month, giving each and every job detail with a job ID and user, when it started, when it ended, the number of GPUs it allocated, like this job allocated 16 GPUs, means 2 nodes it has used, and then equivalent GPU hours, and we sum that up. So this is how we are actually sending the monthly utilization or the statement of account to for every project to every CI project. Moving further, now we what I have is the various images or the photographs. So most of you must be just interacting with us over an email or through you are interacting with the system through a CLI, but however many of you are curious to actually see how physically these systems look like and what are the data centers, how the servers and systems supercomputers look like. So this is a panoramic view which is taken of the Param Siddhi AI and AIRAWAT POC. So you can see AIRAWAT POC on my left side and Param Siddhi AI on my left side and AIRAWAT POC on the right side. These two are actually they are housed in a L-shaped fashion, and these two data centers are part of one National Param Supercomputing Facility data center. though being two different systems. So this is actually the physical view of the Param Siddhi AI system. You can see there are 11 racks in the system spread across a single row, and then we have 7 number of racks actually for housing the DGX A100 nodes. One rack is for a director class switch, 2 racks for the storage, and 1 rack for the ancillary periphery servers and orchestration and inline and out of band management. Each rack is having 6 numbers of DGX A100 nodes and such 7 racks, so total 42 nodes we have. And on top of each rack, you can see these vertical lines. They are nothing but the power cables. So upper side is a false roof and the bottom is a false floor, and these are the perforated tiles. And this is that data center lift which we use to move the servers in and out of the data centers and mount them on the rack and unmount them when we need the maintenance to be carried out. Okay. And this is a view of the AIRAWAT POC data center when it was getting commissioned. That's why lots of cables and laptops you see. The top left side, you can see that there is a tray, right? So that's a more what I can say more highlighted view of the tray, where it carries lots of cables from Param Siddhi AI to AIRAWAT POC, because we have this integrated system, and the director switch is part of the Param Siddhi AI data center, and all the compute communication cables have been actually routed from Param Siddhi AI to AIRAWAT POC, and that's how we have integrated the system. So lots of cables routed across the system. So here also you can see the perforated tiles, and here 10 numbers of racks, each rack housing 4 number of A100 servers, NVIDIA A100 servers, so total 14 numbers. This is a rear view of the racks that you see, and you can see lots of cables. The first one being the rear view of the director switch, wherein you can see lots of cable going into each leaf of the switch, and then the blue color and the red color are nothing but connections for in and out of the coolant, and the bottom side you can see the CDU backside, the coolant distribution unit backside. So this level of cabling is required. This is just a compute communication part of the cabling that is present. The second rack that you see is one of the racks of the storage, and lots of cabling here for storage interconnect. The third one is nothing but the rear view of the DGX A100 compute racks. You can see mix of power and network cables. The rightmost view is the rear view of the rack, where we have all the management monitor, in-band, out-of management, periphery on orchestration network and other ancillary services servers, and that rack is dedicated. You can see lots of dense cables, the LAN cables, which are actually being used for in and out of band management. Lots of cables here as well. These are the pictures of the cooling infrastructure that we have. The left side being this is a rear door heat exchanger based cooling technology. So we have total 17 number of 17 numbers of racks which houses the A100 nodes. So A100 being a very what we can say power hungry and a very dense compute infra. To cool these very dense compute and very power what we can say a huge power consuming infra, the cooling required is a very special purpose and very efficient cooling. So here we have a RDHX, rear door heat exchanger based cooling mechanism to all the A100 all the racks which are housing the A100, and they are 17 in numbers. So here actually the water is being circulated through these rear doors of the RDHX, and then the fans are there which actually suck the hot air out, and then and release the ambient air out of the data, release the ambient air in the data center by cooling it, and that is how the cooling is maintained in a very efficient way. And the other cooling technology that we have is the traditional air-based cooling, which we have the 40 tons of cooling that we have. So each RDHX unit is actually cooling the 40 kilowatts of rack density, and we have 17 numbers in across 2 data centers, and these 40 tons of air conditioners in each of the data centers, so total 80 tons of cooling across 2 data centers through this precision air conditioners. So we have mix of these because RDHX caters to the cooling needs of the DGX 800s. However, for storage and ancillary services and servers and switches, we have this air-based cooling, which is 40 tons of PAC, precision air-based cooling on each of the data centers. Moving further, this is a pictorial view of the data center. The left image shows the entrance of the data center, and the right image shows the path to the data center. Okay. And both the systems, they coexisting in this NPSF data center. To support this 410 AI petaflop huge system, we also require a very what we can say very strong the non-IT, which is a electrical and cooling infra. So we have a transformer of 2 MVA and a dedicated and a diesel generator set, and then UPS for catering to the power needs or the electrical needs of the these 2 systems. And this transformer and DG sets, they also carry the load of the C-DAC building as well as these data centers. Whereas these UPS, they are dedicated for UPS and battery bank, they are dedicated for this systems. So whenever the state electricity goes off, we have this fallback mechanism wherein the entire electrical load is first shifted on to UPS and then further on to diesel generator sets. So we have to maintain the diesels in diesel tanks to run the systems even in the absence of state electricity. So we have 800 kVA UPS, 2 megawatts of diesel generator set, and 2 MVA transformer. And these are the few pictures of when the system was commissioned, the director switch and this director switch commissioning, the racks establishment, and then how the switch was actually getting commissioned. We have many more pictures, but only some are actually added into the presentation, and how we have populated the NIC cards and other components in the servers, and how they have been rack mounted, how they have been carried out with the help of this data center lift, and then commissioning and actually configuration of the system and integration. So with that, I come to the end of this talk, and I thank all of you for actually listening to me patiently, and further questions and answers are welcome. So now the session is open for Q&A, questions and answers. So let me announce the closure of today's session, and the further sessions are actually as per the planned schedule. And tomorrow we have the session as per the plan, and it will start at 10 a.m. So thank you for being us, and have a good day.
Yeah, thanks everyone. So just a small reminder, we're going to use the same link even for tomorrow's session as well. Yeah, and please feel free to post your questions. We can still wait for some more time. In case you have anything, maybe you can post it.